So welcome very much from clear to our webinar tonight of Clear Skies to Stormy Seas. This is Deb Marlor, Captain Deb Marlor with Sailing and Boating LLC. And I am so pleased to be here. I have my guest speaker, Alex Avalos with WRI, Weather Routing Inc. And Alex is a senior meteorologist there and operations manager. And we have had the opportunity to work with WRI for the last almost 2 years. And so the information that we wanted to give to you will be so useful. And that is the most important and critical piece, is that you walk away tonight with useful information. So let me talk to you a little bit about what Alex is going to be sharing with us in the agenda. And so we are going to be talking about some weather basics. So we're going to be learning weather basics, and we're going to be able to understand the surface analyses, and we're going to analyze local weather observations. So when we're on the water, we're going to be able to take a look at what's happening around us, and we'll be able to make observations and determinations as to what we want to do. We'll be able to interpret different cloud types. So we'll have these reminders, what kind of clouds do what. And then we'll be looking at radar and satellite imagery. And then we'll be talking about to-go or no-go recommendations. Whether or not you're a day sailor or a cruiser does not matter. You've got to make this decision. So if you're looking at it for a day or you're looking at cruising for a period of time. And so we'll go into that in depth. Alex is also going to be speaking about the multiple sources for weather information, as well as why you would want to work with weather services, with a weather service. What are the pros and cons? And then we'll break out and we'll have a couple of questions and answers. So please put your questions into chat, and then we'll go through and we'll come back at the end of the presentation and we will answer those questions. And whoops, I want to go back. Here we go. Alex, you are here. So I'm going to actually stop sharing my screen. I would like to bring to you Alex Avalos, and he's going to take 1 second to get his screen going. And so just give us 1 second and away we go.
All right. Host disabled participant screen sharing.
So we want to make you host. So
Perfect.
are you make host? Yes. Okay,
There we go.
Yeah.
Now we're on the move here. All right, Deb. So thank you so much, for hosting this event and putting it together, so that way we could be here to talk about weather basics and the general knowledge that you need to make informed decisions for sailing, whether it's local or offshore. Definitely happy to roll along with this discussion here, and let's get started. So a little bit about me, as Deb had briefly mentioned. I'm an operations manager at Weather Routing Incorporated, as well as a senior meteorologist. And tonight's topic is going to discuss weather basics for boaters. Before we get into more detail about, some of those weather basics, a little bit about where I work. We're a company that's been in business for over 60 years. We were founded by a gentleman named Bill Kasich, who lived in New York City at the time. And over the course of the past 60 years, we've migrated north along the Hudson River to now a little town called Glens Falls, which is about an hour north of the state capital, Albany. We provide forecasts for yachts, sailboats, and sport fishers in our yacht division. We also have a second division called the commercial division, which specializes in cruise ships, commercial vessels, and marinas. And we do provide forecasts and routing advice to clients. We do offer specialized reports as well. Those can range anything in the form of climatology studies, marina forecasts, fishing rallies and regattas, things of that nature. So while our standard service is providing customized forecasts and routing from point A to point B, we do also specialize in tournaments as well. So some of the topics that we're going to go over tonight The basic what is weather and what is climate. We're also going to go over how to interpret charts and maps and go over surface pressure. These are very useful for being able to create a self-weather briefing. We're also going to go over how to interpret observations and how those can also be used as a key towards creating a self-weather briefing. We're also going to go over radar and satellite data. We'll go over some of the different types of satellite data, what the pros and cons of each are. We'll also go over cloud regression and explain how the behaviors of the clouds can give you clues to what kind of weather might be on the way over the next 24 hours and beyond. We'll also go over another important discussion point, ocean currents, and this is especially the case for sailing vessels, but all yachts of any type. Currents are very important to discuss, but considering many of you here are sailors, that point is very important to discuss as well. We'll also go over, choosing weather sources and having multiple sources as well. We'll go over some strategies for local sailing and offshore sailing closer to the end of the discussion. We'll also go over go and no-go recommendations and how WRI can assist you with those, especially if you're in a sensitive situation. And at the very end, there will be a brief sea weather demonstration to go over our supplemental service. So without further ado, let's go ahead and get further into the discussion here. So what drives all weather? Well, the answer to that question is that bright orangey fiery ball in the sky, the sun. Basically what happens is the sun emits shortwave radiation towards the surface of the earth, and that creates heating on the surface of the earth. But what makes the weather basically move and what drives the weather is uneven surface heating. So at the equator, the location with the most direct sunlight is also going to get the most direct heating. Closer to the poles, the more indirect the heating becomes. So what happens there, when you have that uneven heating, it is redistributed across the planet. So it's usually what will happen is it'll be redistributed towards the poles, whereas colder air near the poles will be redistributed towards the equator. And so what happens is, you get that convergence of these different air masses, and that's what gives rise to individual air masses as well. So taking a look at North America as an example, you can see that air masses originating in the northern latitudes tend to be polar air masses or Arctic air masses. Those developing in southern latitudes closer to the equator tend to be tropical in origination, and they may be maritime or continental type tropical air masses. And when you get these convergence of these air masses, what happens is you give birth and rise to cold fronts and warm fronts and other frontal boundaries. So the collision of these air masses produces the fronts, as I said. And when you get these fronts in place, that can also result in the development of thunderstorms or other types of weather. And the larger the difference between temperatures on either side of a boundary, the stronger the front is. And when you get a stronger front, that usually results in stronger to severe weather. And basically, weather is driven by our movement into and out of these air masses. So a little brief discussion on climate versus weather. Weather focuses primarily on the here and now. In the short term, over, say, the next week to couple of weeks. Climate focuses more on the longer term and the general average of weather that's occurred over a very long periods of time. And we can be talking weather on the order of hundreds of years in the past. So one of the best ways to evaluate temperatures, as an example, is to take a look at the Köppen-Geiger climate classification system. And you can see that there are subcategories for this type of climate characterization. So climate A is for equatorial regions, no surprise there. You can see across Ecuador, Peru, and even Brazil. Those locations are located in more equatorial latitudes, and then further east across Central Africa. But generally closer to the poles that you get, the cooler it becomes. So B is arid, C is warm, and warm basically is indicated by the green. Snow is blue. And then polar is these grayer areas, as you can see across the Arctic Circle and closer Antarctica. So basically, when we're looking at a shorter term forecast, that's going to be related to forecasting the local weather. But if we're looking at longer range averages, we're going to be discussing climate. So now we're going to go on to a discussion about surface charts. And these display the numerous weather features that may be present in a given location at any given time. The most common features that you'll see on a surface chart include areas of high and low pressure. You'll also find cold and warm fronts, as well as tropical systems and troughs. And we're going to go into a bit more detail about what each of these features is and coming up in the presentation. But it's always a good idea to have, a surface analysis can give you a really good understanding of what's going on in the here and now, and understanding where these features might move to better understand what's going to happen in, say, the next 24 to 48 hours. So it's a really good tool to use to create your own self-weather briefing. And now moving on to a surface analysis here. As you can see, it is a busy map because there are many features to discuss here, but I'm going to go over some of the most prominent ones. You can see there's a gale here. I'm circling it right now in the Hudson Bay. That's basically another term for a strong area of low pressure. You can see that there's a cold front that's meandering from this gale out of the Hudson Bay across northwestern Ontario into the high plains and upper Midwest of the United States. You can see that there's also a warm front propagating outward from this gale that's extending across western Quebec. Other types of fronts include the stationary front that extends across North Carolina and the Outer Banks down into interior portions of the Deep South. You can see also that the H denotes areas of high pressure. So really, you can find a wide variety of information on a surface analysis. Sometimes these maps can be quite busy, and other times not so much. It all depends on how active the weather pattern is. And one other feature I should mention here on this map that I did not mention already is the trough. And you can see that's denoted by this dashed brownish orangish line that I'm running my cursor across here. And it's located in the Labrador Sea down across St. John, Newfoundland into the south of Nova Scotia. So moving on to areas of high pressure. These are associated with benign and calm weather conditions. Areas of high pressure tend to be semi-permanent. A very good example of a semi-permanent high pressure is the subtropical ridge across the central Atlantic, and it extends ridging southward into the Caribbean across the Virgin, Leeward, and Windward Islands. Areas of high pressure themselves tend to flow clockwise in nature, or as we like to say in meteorological terms, anticyclonic. Now, in the Northern Hemisphere, it varies from what you would expect in the Southern Hemisphere. It does exactly the opposite in the Southern Hemisphere, and areas of high pressure rotate counterclockwise in the Southern Hemisphere, or cyclonic, as we say in meteorological terms. And weather in association with areas of high pressure tends to be calmest near the center of the high. Now, as you get outward from the center of the high, you'll tend to see more isobars and stronger winds that tend to develop and occur the further away you are from an area of high pressure. But usually the weather is not going to be stormy in association with a high pressure. It has the potential to be windy, but we're not really talking about anything in the way of thunderstorms or severe weather in that nature. And so here you can see there's a broad area of high pressure centered over south central Quebec and northwestern Maine, with isobars very spread out across New England and down to the Delmarva, even across much of Quebec and into southeastern Ontario. Now, the further away you move from the high, you'll note that there are more compact isobars across central Ontario. This indicates stronger winds and less benign, if you will, than closer to the center of high pressure. So now going into the transition from areas of high pressure to areas of low pressure, weather in association with low pressure tends to be very stormy. And this is especially the case near the center of the low. Now, in the Northern Hemisphere, areas of low pressure tend to flow counterclockwise or cyclonic. In the Southern Hemisphere, these lows tend to rotate clockwise or anticyclonic. And the isobars tend to be more tightly packed than they do with their high pressure counterparts. And certainly these lows tend to be a bit more deep than areas of high pressure. And certainly the deeper or stronger the low, the more intense they are, and the more intense the weather can be in association with them. So the storminess tends to decrease with outward extent from the low, but because you get the isobars more tightly packed together, stronger winds can prevail across greater distances from the center of the low than they normally would for areas of high pressure. And here's an example of an area of low pressure over the lower Mississippi River Valley across northwestern Mississippi. And you can see that there's a bit of a warm front / stationary front extending across the lower Tennessee River Valley and into parts of the deep south of the United States, and a cold front extending across the lower Mississippi Valley and offshore southeastern Texas. This area is known as the warm sector. And basically within the warm sector is a region of unstable tropical air that gives rise to the development of showers and even thunderstorms. And thunderstorms can be pretty significant within areas of within the warm sector. So wherever you encounter a warm sector, it's always good to be cognizant of the fact that you could be encountering severe squally weather when those develop. So now moving on to cold fronts, as I briefly touched on just a moment ago. Basically what these are transition boundaries. And what happens is the cold front is generally the leading edge of a cooler air mass. And what happens is this leading edge of cold air overspreads warm, oftentimes moist and tropical air. And what happens is you get that density difference between warm, moist tropical air, which is not very dense at all, and cold, dry air, which is much more dense. So warm tropical air will tend to rise and be replaced by cold, drier air. This gives way to condensation and results in showers and thunderstorms. And in association with cold front passages, these thunderstorms can be significant. As I said, another thing that can be significant ahead of a cold front are the winds. And usually ahead of a cold front, the winds will be out of the south to southwest. But when a cold front moves overhead and then passes a particular region, they'll tend to veer around to the west to northwest, and basically ushering in a cooler, drier air mass. The triangles, as you see on this diagram, indicate the direction in which the front is moving. So this front is moving in a southeasterly direction. And here's an example of a cold front extending from roughly New York City and eastern New Jersey down across the Delmarva region into interior portions of the southeastern United States. And as you can see, the movement of this front is variable just based on the sense that it's a pretty extensive cold front extending from the mid-Atlantic down to the deep south. So basically from New Jersey down to North Carolina and northern Georgia, the front is moving generally southeasterly, whereas from northwestern Georgia across Alabama and Mississippi into Arkansas, it's moving more in a southerly direction. Now, warm fronts have the opposite effect of cold fronts, and there are definitely some notable differences between the two types of frontal features. The biggest difference is where the name comes from. Unlike cold fronts, which usher in colder air, warm fronts are the leading edge of a warmer air mass overspreading a colder air mass. And what will happen with the warm front passages is you usually get steady rainfall or precipitation occurring. Now, while it's not rare, it's relatively uncommon that thunderstorms develop with warm front passages. It still does happen, but much less than their cold front counterparts. And as these warm fronts usher in warmer air, the humidity tends to increase with these warm front passages, in part because it's ushering in a more tropical, moist air mass. Winds in association with a warm front passage will generally start out northeasterly, but then gradually veer around to the east to southeast, which basically is opening the floodgates for warmer, more tropical air to overspread a given region. And unlike cold fronts, high winds tend to be very rare with a warm front passage. Now, the red semicircles that you see on this map indicate the motion of the warm front, and this front is moving in a generally northwesterly direction. And here's an example of a warm front on a surface map extending from the lower peninsula of Michigan down to the Delmarva region. And as discussed before, the red semicircles indicate the movement of this front. This front is moving generally northeastward across the northern Appalachians of Pennsylvania, and eventually will be moving into New York State and across portions of New England. Now, another type of front is a stationary front, and these are denoted on a surface analysis with a combination of both cold front triangles and warm front semicircles. These fronts tend to be, basically what happens is a stationary front results when a cold front and a warm front converge. And because they're moving in opposite directions, when they converge, there's really little in the way of movement thereafter. However, the convergence of these two fronts can result in lift, and that can serve as a focus for developing rain. And now usually you won't see significant thunderstorms with developing stationary fronts, but they can occur. At the same time, thunderstorms tend to not be nearly as significant as they do with cold front passages. And here's an example of a stationary front extending across parts of the Central Plains, across the state of Kansas, and into central and eastern portions of the state of Colorado. My cursor is highlighting this front here, as you can see. Now, occluded fronts occur when a faster moving cold front tends to overtake a slower moving warm front. And what happens is, as the cold front overtakes the warm front, that warmer, more moist air mass is shoved aloft, and the cooler, more dense air sinks to the surface. And basically, it's also noted as a boundary of cold air that's overtaking, less cold air. We'll call it cool instead of warm, but it's definitely colder than the air mass it's replacing. And certainly it's basically a hybrid type of front, as you can see. The warm front and the cold front will move in the same direction, and the triangles and circles indicate the movement of this front. And in this example, it's moving northward. So I'm going to point to the occluded front that you can see on this map extending from Cape Cod down to offshore of the mid-Atlantic. Basically, this cold front that you see extending down to Florida had overtaken this warm front that's extending offshore and closer towards Bermuda, or in the direction of Bermuda, I should say. So basically, the cold front overtakes that warm front. And in the top left-hand side of the screen, you can see another example of an occluded front across the northern high plains across eastern North Dakota. Now we're going to move on to a discussion about troughs. Troughs and fronts have similar characteristics, but there are some notable differences. Troughs are basically elongated areas of low pressure that extend outward from areas of low pressure. And they tend to form on the backside of these lows. Now, the biggest differences between a trough and a cold front, for example, is the fact that there's very little in the way of a temperature change with a trough. Both a front and a trough are associated with a notable wind shift, but there's no difference in the temperatures really, and if there is, it's very negligible. With troughs, you tend to get showery weather. Strong, severe thunderstorm activity is not as common with troughs as it is with cold fronts. But certainly it can usher in unsettled weather. And that's certainly something to be cognizant of, including the possibility for a few thunderstorms here and there. And on this map, you can see here's an example of a trough extending from southeastern Massachusetts down across the Delmarva and outer banks of North Carolina into interior South Carolina. You can see here, the isobars basically indicate a southwesterly wind ahead of this trough, but behind the trough, it's more of a north to northwesterly wind. And an honorable mention for a trough extends across central Quebec and into southeastern Ontario. And there's a little bit of a wind shift here that you can see across western Quebec. So moving on from surface analyses to the upper levels, this is an example of a 500 millibar chart. Basically, there are a couple of things to note here. You can see a strong trough digging into the Delmarva in southeastern US. This is associated with unsettled weather. Now, across the western half of the United States, you can take note of this ridge that's in place. And while there's unsettled weather going on across the eastern half of the United States, weather across the western half of the United States tends to be more benign and settled. And these troughs are very important in evaluating cold front movements, as well as the movement of highs and low pressure, because these winds aloft are what generates the movement and progression of highs and lows, as well as fronts and troughs. You can see the arrow points to the trough itself. So now moving on to wind barbs, which are very common on a surface analysis. There's some things to note about wind barbs, right off the bat. There are differences between wind barbs and wind vectors. Wind vectors point to the direction in which the wind is moving, but the wind barbs point to the direction in which the wind is coming from. So when you see a full barb on a wind barb, it's equivalent to 10 knots of wind. A half barb is equivalent to half of that, so 5 knots of wind. So when you add the barbs up, 10 knots and 15 knots, you get a 15-knot wind speed, or 17-mile-per-hour wind speed. And because this wind barb is pointing to the west, that means the wind is coming from the west. As far as a flag on a wind vector, you can see here that's indicated by a 50-knot wind. And because this wind barb is pointing south, that means the wind is coming from the south at 50 knots or 58 miles per hour. And in this example, we have a combination of a flag and full and half wind barbs. So you do the math on this. A flag is 50 knots. A full barb is 10, that's 60. Another full barb, that's 10 and 70. And then a half barb, which is 5, gives you 75 total knots or 86 miles per hour of wind. So when you're reading a surface analysis, always keep that in mind, that there are distinct differences between wind vectors and wind barbs. So now moving on to the Beaufort scale. There are multiple classifications here on this table, from force 0, which is basically minimal weather, no concerns at all. The seas are almost smooth as glass. There's very little in the way of wind, to force 12, which means a hurricane or significant wave heights. Visibility can be quite terrible as well. This was developed in the early 1800s by Sir Francis Beaufort in the absence of weather tools and instruments. But basically what it does is it gives rise to being able to estimate what the sea state might be with the wind. And certainly, with more tools available now, there are other features that can be used to measure wind speed and sea height. But certainly this is a good way to estimate as well. And so now, in understanding whether the weather is going to improve or get worse, a barometer can give you some tips and clues as to what the weather is going to do. So there are two different types of rules, including the 1, 2, 3 rule and the 4, 5, 6 rule. Now, when the pressure tends to fall in the 1, 2, 3 rule of 1 to 2 millibars in 3 hours, yes, that tends to indicate that the weather is deteriorating, but it's not deteriorating at an alarming rate. But at the same time, it's worth keeping an eye on, and you should be aware that more significant changes in the weather may be on the way. Now, a more volatile scenario would involve pressure falls of 4 to 5 millibars in 6 hours under the 4, 5, 6 rule. You should have plans, to take action to avoid worsening weather, because it's going to be deteriorating at a significantly faster rate than if it's 1 to 2 millibars in 3 hours. So moving on to buoy reports, this is the start of the evaluating and assessing local observations. There's a lot of good information on the National Data and Buoy Center website at NOAA. Sea buoys tend to give a wealth of information that are really helpful. There's buoy information worldwide. The data is quality controlled, so there's no erroneous information, that's in place on these buoys. At least that's not, allowed to be displayed. Certainly, if a buoy is out of commission, the National Data Buoy Center makes that known. But certain things that are noted on a buoy include the date and time, as well as the wind direction and speed, and any notable gusts. It'll also talk about what the significant wave height and the most dominant wave periods are. It'll also talk about what the average wave period is and what the average wave direction is as well. They even let you know if the pressure is rising or falling. So in this example alone, you could infer that the weather's improving. The air temperature here is shown, as is the dew point and the sea surface temperature. One of the other pros about buoys as well is that they're stationary and they remain in place. So basically it's easier to evaluate trends with sea buoys because they're not really moving. Which brings me to my next point. So on the National Data and Buoy Center website, you can view the hourly observations at a given buoy over the course of 24 hours. And in this example, so you can use these to evaluate the trends at a given buoy. And as you can see, there's really not much in the way of significant pressure changes. Similarly with the wind speed and gusts, as well as the wave heights. So basically you can infer just reading, these observations that the weather has not changed much. These hourly reports can also help you to put together a self-weather briefing and give you an idea of what's coming down the pike. And certainly having a surface analysis, that certainly would help as well. But it's very useful information to get the information on what's going on in a given location over a period of time. Another type of observation can be found on ships. Now, unlike their buoy counterparts, this information is not quality controlled. So certainly the possibility that you're going to encounter more erroneous observations does increase versus with a buoy. And another thing that can really throw a wrench into the accuracy of an observation is based upon where that ob is located on a vessel. Now, a vessel that has an ob at the top is certainly going to be subjected to higher winds than one that's at deck level. So another limitation from ship observations is that they're always moving. Weather can change over distances, and it's not exactly giving you the most accurate picture as to what's going on over a given location at a given time. But they do provide a lot of the same information that buoys do, including what the wind speeds and the wind directions are, if there are any pertinent gusts. You can also get the wave heights and the periods from those. They'll also let you know what the visibility is, including what the temperature and dew point are. Some of them will even give you sea surface temperatures as well. But it's certainly, in spite of its limitations, can be a very useful tool in determining what's happening in the here and now at a given location. And I would say with ship observations, it's always good to look at surrounding observations as well, because the possibility of erroneous ship data tends to be higher than that is the case with sea buoy data. Another unique tool is the ASCAT tool, which basically involves a satellite that's orbiting the Earth twice a day. It's a polar orbiting satellite, and you can see larger swaths of a region and get the wind speeds that way. And basically the way that the ASCAT measures wind speed is based upon the wind-driven seas. There are some limitations to the ASCAT data as well, and you can see it very clearly on this map. There is a wide swath of observations from eastern Long Island across Cape Cod and into the Gulf of Maine. But because the satellite scans certain strips of the planet twice a day, you're going to note that there's absent data missing in other parts too. And as evidenced by this map, you can see there's really nothing that we can infer as to what's happening across Nova Scotia and across New Brunswick and Prince Edward Island. So it's always good when you're looking at local observations, take all of your tools and look at them together to come up with a consensus as to what the latest trends are, especially considering the fact that with ASCAT, it's not updating regularly like a lot of these observations are. And so now moving to the radar, this helps to measure precipitation intensity. It also is a very good tool to indicate where precipitation may be falling at any given moment. And of course, to help the user understand where the precipitation might be lightest and heaviest, basically the radar is color coded. And so where you see these cooler green, blue colors, usually the precipitation is falling at lighter rates. But when you get into the hotter colors, such as the yellow, the orange, and the red, that indicates more intense precipitation. And where you get the intense precipitation is where the thunderstorms are more likely to be and more widespread. So here's an example of an arrow pointing to a cluster of thunderstorms located in the northwestern Gulf of Mexico, offshore of southeastern Texas and southwestern Louisiana. So across the United States and US territories, there are 160 radars. There's also additional availability worldwide. There are some limitations to the radars that exist in that one single radar can only see out to 290 miles. But however, the good news is that the radar network is set up so that next door neighboring radars can pick up on the range that a radar might not be able to see on its own. And it provides ample coverage across the United States and other parts of the world to make sure that all weather is being covered, by this network. Radar is also very useful for indicating what would rightfully be a mariner's worst nightmare, or one of them, I should say, tornadoes and waterspouts. So these two features are pretty much the same thing, but the difference is that tornadoes occur over land, waterspouts occur over water. But it is all true that waterspouts that can move ashore and become tornadoes and vice versa. So usually what will happen is you'll see these waterspouts and tornadoes occurring with supercell thunderstorms, as evidenced by this comma-shaped thunderstorm. There's a thunderstorm approaching Godric with what's likely to be a waterspout. And when you're looking at radar for tornadoes and waterspouts, it's always a good idea to look at velocities too, as indicated by this radar screenshot on the right. You can see that there are different varying colors. Basically what happens to find the circulation is the cooler temperatures will move away from the radar. And in this case, you can see I'm pointing downward where the cooler temperatures are pointing away from the radar. And you can see there's some orange and reds in here on the east side of Godric, which are pointing towards the radar. So that basically creates the cyclonic movement with a tornado, or the cyclonic movement that is needed for a tornado to develop. And based on this image alone, we can't confirm that there's actually a waterspout that has touched down. But the signal is very strong that it's very favorable that one could touch down or may already be on the ground. So pulling up the arrow, the likely waterspout is embedded within this comma shape on the south side of the supercell approaching Godric, Ontario. So moving on to satellite imagery, this tends to focus more on cloud cover than it does rainfall intensity. There's two types in particular that are most common and popular, and that's the visible and infrared satellite imagery. And both of these can find areas of thunderstorms and weather features, although there's pros and cons to each. Visible satellite imagery in particular can find outflow boundaries, which are basically like mini cold fronts. Let's go into more detail about what you can get from visible satellite imagery. So visible satellite imagery allows you to see this types of clouds and also get a good understanding of what the structure of those clouds might be. Certainly the structures tend to be more dynamic with respect to thunderstorms than they do with cirrus clouds and the like. But it's really high resolution, and it's great to be able to view any cloud structures that might be in place. But there is a severe limitation to visible satellite imagery in that you can only use visible satellite imagery during the daylight hours. At night, once the sun's set, it's absolutely rendered useless, for lack of a better term. You can find visible satellite imagery on a number of websites, including NASA and the GHCC website, as well as on NOAA. Those are just some of the places that you can find the various types of visible satellite imagery, including GOES, Himawari, which is more common out in the Western Pacific, things of that nature. And here's an example of a cluster of thunderstorms across, the Lesser Antilles, northward across Canouan, where Deb is for this webinar, and into the Leeward Islands. And you'll note there are a couple of thin bands shown here, but I want to point your attention to this little thin band, most notably across the Leeward Islands, because of this cluster of thunderstorms occurring here. So the outflow boundary tends to find itself out ahead of a cluster of thunderstorms and generally moves away from those clusters. So this arrow will tend to point to where this outflow boundary will be. But as I said, that's not the only one in this image that you can see here. There's clearly a few more that are very visible on this satellite image shot, and I'm circling them right now. So there's another, and off here on the edge of the screen, there's another outflow boundary. So a more zoomed in view of visible satellite imagery meant to be able to find some thunderstorms. And you'll note here that there are some popcorn-esque type structures here. That's also another good clue that there will be thunderstorm activity. And basically, the taller the clouds, the whiter they will appear, on visible satellite imagery, the puffier they'll appear. So you can see the arrows pointing to this location here. Visible satellite imagery is also very useful for finding fog. And it's the only type of satellite imagery that can be used to find fog banks. Fog banks look smoother in shape and size than thunderclouds, than cumulonimbus clouds do, and they tend to be grayer. And generally, the movement of these fog banks tends to be smoother as well than their cumulonimbus counterparts. You can see that there's a well-defined area of fog outside of the Gulf of Maine and across western Nova Scotia, out into open waters beyond Cape Cod. And when you put a visible satellite imagery loop into motion, you can see these fog banks clearly moving ever so slightly from one location to the next. And you can see the arrows pointing to that fog bank right there. Now, the other type of satellite imagery is called infrared satellite imagery. And there are some pros to infrared satellite imagery that you don't get with visible satellite imagery. But the most significant and notable difference is the fact that you have access to infrared satellite imagery any time of day or night. Your usage of it is not limited to the daylight hours. Visible or infrared satellite imagery is very useful at measuring cloud temperatures. However, because the resolution is not nearly as good with infrared imagery as it is with visible, you're not going to be able to see some of these finer scale features such as gust fronts or even cold fronts themselves. So that the ability to spot those tends to be lacking with infrared satellite imagery. Now here you can see an example of infrared satellite imagery. These warmer temperatures basically indicate, based on this key, that the cloud tops are taller, and certainly the taller the cloud tops are, the colder they're going to be. So the taller the cloud tops, the more likely we're talking about thunderstorm activity, and that's very evident in a couple of locations here, mostly across the Yucatan and near Cozumel, across southeastern Cuba and Jamaica, and even closer to the Rio Grande Valley from Texas into northern Mexico are just some of the areas where thunderstorm activity is occurring, as evidenced by taller cloud tops. Now, furthering the discussion on clouds, you can use the movement and behavior of clouds to determine, or at least get a better idea of what the weather is going to be like in your area in the next 24 hours or so, or further. Now, there's it's well known that clouds do change ahead of developing systems. Use those clouds, the movements of those clouds, to determine or get a better understanding of what might be heading your way. There's an old cliche saying, but it's very useful at the same time, called red sky in the morning, sailors take warning. Red sky at night, sailors delight. And basically what happens with that is usually when red sky in the morning, sailors take warning is, observed. That means that, weather's going to be deteriorating with time during the day. But red sky at night, sailor's delight basically implies that the weather's going to be improving and getting better. Cumulus clouds tend to be puffy in texture, but they tend to be low-level clouds at the same time. And usually cumulus clouds will occur with fair weather. Cumulus clouds have some moisture, but not an abundance of it. However, when you do get amply more moisture than what is needed for cumulus clouds, they tend to evolve into something more significant. And that tends to be the cumulonimbus cloud. And the cumulonimbus cloud is notorious for developing thunderstorms, those of which can be strong to severe. So basically what instability is you get warm, moist air closer to the surface that rises. It replaces cooler, drier air aloft. And as the warmer air interacts with cooler air aloft, the warmer air parcels condense into clouds and they keep rising. And then once these parcels of air reach a stable layer in the atmosphere or the bottom of the stratosphere, the parcels can't rise anymore. So they have to fan out. And that's what gives rise to the beautiful anvil texture that you see with cumulonimbus clouds. And so, as I said, the instability is a driver of thunderstorm development, and these thunderstorms can be strong to severe. You can even get water spouts with strong to severe thunderstorms and squalls too. So whenever you see cumulonimbus clouds and you're out on the open waters, it's a sign that you could be in for some pretty rough weather, especially if they're moving in your direction. But at the same time, outflow boundaries are another concern too, even if you're not getting hit by the parent storm itself. So ahead of larger scale storms, one of the first types of clouds that you'll tend to see are cirrus clouds. And these are at very high altitudes. Because they're at very high altitudes, there tends to be a higher level of ice concentration within these clouds. But as you get more moisture moving in, the density will increase, at those higher altitudes. That'll result in more ice developing within these clouds. Usually you'll tend to see cirrus clouds occurring 24 hours or less before an approaching storm. That will tend to give way to altocumulus clouds. And with altocumulus clouds, these generally occur within 12 hours of the onset of precipitation. And the behavior of these clouds is characterized by increasingly overcast and a lowering cloud base. So usually you won't see precipitation with them just yet. But you're within that 12 to 24-hour window in which rainfall or any other type of precipitation, be it snow, sleet, or freezing rain, might be filling in across a region. And it's also worth noting that visibilities do decrease somewhat as well, but that doesn't become as much of a concern until the event itself. And usually the most common type of cloud you'll see on periods of unsettled weather is the nimbostratus cloud. Usually that's a good indicator that precipitation is imminent or occurring. When you get that precipitation occurring, and especially if it's heavier, visibilities will tend to lower. Another concern for lower visibility can be dense fog, which can result from the lowering of the clouds, and then in conjunction with ongoing precipitation, which can really result in lower visibility cases. But when the weather begins to improve, the visibility will begin to increase again, and that's associated with a decrease in precipitation. Now, another topic for discussion are ocean currents. As I said at the very beginning, currents are very important for any boater, but especially for a sailor. There are many types of tidal currents and larger currents. The Gulf Stream is perhaps one of the most notable currents, especially in the United States. The Gulf Stream tends to be less subjected to extreme changes based on significant changes in the weather, whereas tidal currents would be more subjected to significant changes when you do encounter those heavy weather conditions. So basically, when you do encounter, quickly deteriorating weather in tidal currents, you can have high variability over a short distance within those tidal currents. So here's an example of the Gulf Stream shown across the Carolinas and mid-Atlantic, branching outward into open waters of the northwestern Atlantic. Some interesting things to note here. The Gulf Stream is basically a ribbon of warmer sea surface temperatures meandering into open waters of the northwestern Atlantic. But there's also these eddies, as you can see, these clockwise and counterclockwise rotating eddies. So for clockwise rotating eddies, those are known as warm eddies. And basically what's happening is warmer sea surface temperatures are replacing cooler sea surface temperatures. The opposite is true for cold eddies. When you get the counterclockwise rotation of the current, you've got cooler sea surface temperatures replacing warm sea surface temperatures. And the Gulf Stream basically acts like a temperature gradient as well. So in this example, you can see the ribbon of the Gulf Stream meandering up into the open waters of the northwestern Atlantic. And those eddies are on full display here. Basically, in the Gulf Stream and south of the Gulf Stream, there's very little in the way of variability with respect to the sea surface temperatures, but obviously the warmest sea surface temperatures are located within the Gulf Stream itself. But north of the Gulf Stream, those sea surface temperatures tend to drop off considerably, especially north of 40 North and into the Gulf of Maine, offshore of Cape Cod and the islands of Nantucket and Martha's Vineyard, and even in open waters south of Nova Scotia. So it basically acts like a temperature boundary in a lot of situations. So now we're going to move on to a discussion about sources. There's a number of things that you should consider when finding a weather provider, whether it's actually working with degreed meteorologists or using apps over the phone or websites on your desktop. Always consider the reputation of the provider. Do they have an accurate track record of providing accurate forecasts? Consider the dedication of the science of meteorology as well. For a weather provider such as Weather Routing, we have over 55 degreed meteorologists on staff. Meteorologists, we have the ability based upon experience, working with weather situations to understand what nuances might be hard for the models to pick up on, and having that knowledge can assist a boater with finding the most accurate weather forecast because the models on their own can be off at times. Accessibility is another important component to considering your source. Do you have 24-hour access 7 days a week? We do understand, of course, that in the boating industry that sometimes, the unfortunate circumstance of emergencies does happen, including with respect to weather. So having that 24-hour a day, 7-day-a-week accessibility is very important too. And even better if you have access to the human element. And accessibility and reliability go hand in hand in a way as well. Those 24/7 operations give you all the access to the information you need whenever you need it. Doesn't matter what time of day or night, or whether it's on a holiday, you name it. The most reliable weather providers will have 24/7 access. For looking at news channel sources, scrutinize on-air talent closely. No two areas of the world are exactly alike when it comes to forecasting weather, and terrain can really play a difference in the forecasted conditions in a given location. So make sure, if you do rely on news channels and news station meteorologists, to really scrutinize their on-air talent and make sure that they have a working knowledge of the local area and how that can drive the weather. So some examples of weather service sources include NOAA itself, the National Weather Service for the United States, but there are also mobile and desktop apps such as Windy and Predict Wind, Buoy Weather. A lot of these sources are limited by the fact that they don't have the human element. And as I said before, the human element has a knack for determining how terrain can affect weather, and the models don't exactly always pick up on this. So, you're limited by the fact that, with some of these mobile apps, that you only have computer models and no human meteorologists whom you can ask questions to. But as I said, there are other types of sources such as weather routers, and that's where we come in. But a little more on that in a little bit. So as far as local sailing and offshore sailing, there are definitely strategies to employ here. With respect to the go and no-go recommendations on your own, it's certainly a bit easier to manage that on your own for local sailing, because local sailing often involves short daytime hops near your home port, for example. So, there are certain considerations you don't need to take into consideration at that point that you would need to for a longer offshore passage. Because it simply involves going out to sail locally and then returning to port that night. And if the weather gets bad, you can duck back into port pretty quickly. Now, for offshore sailing, there are other strategies to employ because of such concerns. With offshore sailing, you're covering a larger area, so the odds that you might encounter rough weather increase tenfold. Some of the things that's worth considering when you sail offshore, especially for sailing vessels, make sure that there's an ample fuel supply on board. You may find yourself in a situation where there aren't winds to sail, and you might find yourself motoring for a large duration of the trip. Because you're covering a larger area as well, it's important to have contingency bailout options over the expansive area that you might be covering, and plan on having flexibility before continuing onward if the weather just will not allow you to continue. So we come in and that's where we can assist you with finding the best windows. We work closely with you to not only strategize the best, departure day and time, but we also work with you to make sure you're on the best route that's going to provide you with the best sailing assist and current assist, giving you the most favorable wind angles, while also minimizing the sea state. Because at the end of the day, we want you to not only be safe, but we want you to be comfortable. So as far as WRI's assistance, where we can, be of the best assistance to you, basically, if you provide us with the maximum wind and sea constraints that you'd be comfortable with, we can provide you with a valid or non-valid departure recommendation. Certainly if either the winds or the seas are going to exceed those constraints you give us, we're not going to validate such a departure because we're keeping in mind the safety and comfort that you asked us to consider. But we work closely with you to make sure that you're finding the best window and that you're also finding the most optimal route. And if you do need to stop along the way, we work with you closely to discuss that further. So here's an example of what one of our forecasts looks like for a vessel that was going from Cabo San Lucas to Hualtuco. As you can see, this is not a departure we validated due to tropical cyclone concerns, as you can see on this map here, southwest of the Baja. So now that we've gone over some of the basics of weather and more information about weather routings, customized routing and forecast service, I'm just going to do a brief overview on our supplemental service, seaweather.net. So let's go ahead and share that on our screen again. All right, so you can see I have an example route here from Canoan, where Deb is for this webinar, up to St. Martin. What I have plotted up here on this map are basically a combination of wind speed and wave heights. And the wave heights are denoted by the colors. The wind speeds are denoted by the vectors. So basically what happens is when I go ahead and calculate this route that I have out here, what it's going to do is it's going to show me the thresholds and the certainties with respect to the forecast for the winds and the seas. So bear with me just 1 second here. So you can see that the route is highlighted in green and in yellow at times. Basically what this means is that when the color is green, that the confidence in the conditions is higher. And this has to do with the fact that this time period is in the shorter term. And as you get closer to departure time, the accuracy increases and so does the confidence. The further out you get, as evidenced by the yellow, the confidence does begin to slowly decrease because the forecast becomes increasingly longer range in nature. And so you can see here, just looking at this table on the left-hand side, it shows you the latitude and longitude of the vessel at the expected given times. And even if you hover over it, it'll tell you what the forecast confidence is with respect to the winds and the seas. And as you can see, it is model predicted. Other parameters that you can plot up include, the currents. As I said, that's a very important one for sailing vessels. And that's denoted here by the different colors that you can see on the map. You can also pull up the squall threat index, which will give you a clue as to the severity of squalls that you might encounter or how severe they might become. You can also plot up the radar, stimulated radar across a given location and cloud cover. You can also plot up sea surface temperatures. So there's a wide arrangement of resources here at seaweather.net, including Seaweather Onboard, which basically has a similar function to the Voyage Planner, but you can download data files up to 4 times per day in areas of limited internet connection. But I think one area of SeaWeather that's really notable, especially for this time of year, and as we head into the peak of the Atlantic hurricane season, is the Tropical Tracker. And when you have access to the Tropical Tracker, you can see a daily tropical summary for a given basin. So it basically looks like this. And you can see basically here we have the remnants of subtropical depression Don meandering across open waters of the Central Atlantic. You can also highlight and hover over the specific systems to get a summary of what's happening with the particular system in question. And it's meant to keep you safe and well informed during the peak of the Atlantic hurricane season. We also do have a fishing planner in association with SeaWeather for those who are interested in fishing and finding hotspots for particular species of fish. So bringing it back to our PowerPoint presentation, let me pull that back up right here. If I can get that screen back up on the screen. Here we go. Basically, this is our contact information. You can contact us at this phone number or this email address at the bottom. As I said, we are available 24 hours a day, 7 days a week. So it doesn't matter what time of day or night, or if it's on the holidays, there's going to be someone here ready to assist you at all hours of the day and night. And if you want to learn more about our company, visit us at www.wriwx.com.
And so, frankly, everyone, we want to thank you so much for being here. We did promise you a free gift, and we actually have a couple for you. So first of all, WRI has been so generous. They're giving you 1 complimentary forecast. You can ask for that forecast to be either verbal or in writing. One of the great things that I love about the way that WRI does their coupons and their when they are doing a giveaway like this is they are giving you a couple years to use it. So some of you may be in a position where you're planning to go cruising and you really would like to talk with and understand their services, and you can actually use their services until 7/17 of 2025, as long as you've never used their services up until that point. So what we would ask that you would do is send an email to wri@wriwx.com. And in your subject header, just put webinar attendee with sailing and boating LLC.com. And then they will communicate with you and make sure that you get your complimentary forecast. And in addition to that, I am also going to give you a free gift from Sailing and Boating LLC. And if you have not done any of my courses, I'd encourage you to take a look at sailingandboatingllc.com. But one course that I would love to offer to you that I'm doing September 11th is Jump from the Dock to Cruising. And we go through a whole series of information that will prepare you to leave your marina and to actually go cruising. We usually charge for our classes. This will be free to you as an attendee, and we will be starting that at 7:30 Eastern. And again, all you have to do is email me, captain@sailingandboatingllc.com, and just state that you were a webinar attendee, and we will make sure that you get that offer. And last but not least, I want to thank our affiliate partners. So many of you came to us through organizations like Co-Boaters, Nautic Ed, SunPower, Blue Sail Yachting, Key West, the Cruiser University, Annapolis Boat Show, organization. And I just really want to thank my affiliate partners for putting the information out there. We've had tremendous response. Thank you for being here. And again, most importantly, we can't do this without you. I want to thank you for attending, and I look forward to seeing you in the future. So what I wanted to ask you about, well, I'm bringing up the next, is I have a couple of questions for you. I wanted to ask you about the Beaufort scale. And the Beaufort scale, you said, was actually developed in the 1800s. Now, you showed us the scale with just the wave heights and the winds. But one of the things that I always thought was fascinating and is so darn accurate is the what I see on the water. So reading the water from the winds. And so it has been absolutely incredibly valuable to me. So here we are, we're using a tool today with all of this technology, and it's a valuable tool for our sailors. Is that correct?
Yeah, absolutely. And, I think one of the biggest takeaways is, adding on to the accuracy of the Beaufort scale. One of the things that can really be useful for sailors is, understanding the ratio of the wind speed to the wind-driven sea state. So one rule of thumb that I use as a forecaster is for every 5 knots of wind, that's going to equal 1 foot in wind-driven seas. So a 15 to 20 knot wind is going to be equivalent to 3 to 4 foot wind-driven seas. Certainly, of course, back in the day, there weren't the same tools that there are now, and forecast accuracy has increased since then. My experience in working with clients who do use the Beaufort scale, my understanding is that they find it to be accurate, as you state as well.
Yeah, absolutely. I do have a question for you because of where we are located. Being that we're in Kanawha, we're in the actual Windward Islands. There is a conversation that constantly is going on about how the Sierra Sands affect the weather that we have and what is coming off of Africa. Can you speak to that a little bit for the people who are sailing in the Caribbean and how that weather is affecting us here in this part of the Caribbean?
Yeah, so with respect to the Sierra Sands, the biggest impact that it tends to have on the Caribbean is it basically suppresses tropical activity. That's what you want to have happen. So when you see the Sierra Sands moving towards the Caribbean, that's actually really good news because it limits tropical development. And what you need for tropical cyclones to develop, you need warm, moist air aloft. You need warm sea surface temperatures and light winds aloft too. But basically what happens when you have the Saharan dust, if you will, that basically chokes the moisture in the upper levels that is needed for these cyclones to get going. So you can definitely have, uber bath water in the Caribbean, but if you don't have the moisture in place, any tropical cyclone that develops or any cyclone that tries to develop is not going to get very far. So that's, the dust emerging from Western Africa is definitely a godsend, if you want to call it that, to mitigate tropical activity.
Perfect.
That's the biggest way in which it's impacted.
Well, we do have uber warm water, excuse me. Our water is about 88 degrees here. So very different than what is being experienced up in New England.
Yes. Very different.
One last question. So I was curious if you could talk about why, because so many of our viewers tonight are from the eastern part of the United States, and a lot of people are from Florida. Why does Florida consistently have such severity in their thunderstorms in comparison to anywhere else that we've really sailed, in comparison to the Bahamas, in comparison to the Caribbean? So could you speak to that a little bit as well?
Yeah, absolutely. And I think that's a fantastic question, Deb. So there's a few factors at play here. With respect to the Caribbean and the Bahamas, basically the land masses there are not very large. Across Florida, you've got a larger land mass with the Florida Peninsula. What happens, especially during the summer when you get the heat of the day, there's a temperature gradient from the mainland of Florida and the surrounding seas. And that temperature difference basically causes what is called a sea breeze. And basically those sea breeze fronts move on shore and they act as a convergence zone, which causes lift and causes the thunderstorms to develop. And they can be quite numerous as well. You don't really have pronounced sea breeze boundaries in the Caribbean and across the Bahamas, where thunderstorm activity tends to be more trade driven or driven in association with the trades. And there's another thing too that occurs in Florida, which is more common during the cooler season months. Occasionally you can get stronger cold fronts that shift across the Florida peninsula. And that can be the reason behind strong severe squalls. And usually when you get these fronts moving towards the Caribbean in the winter months, they tend to make it as far as Hispaniola and then stall out for days at a time. So they're stalled out and they weaken. So, areas to the east, like across the Leeward and Windward Islands, it's still largely trade driven. But even further west, where they may be frontal driven, they tend to be less severe as a result of that. But basically, the biggest difference between Florida and the Caribbean islands is the fact that Florida is a massive landmass. And, there's a greater temperature gradient in existence there between the land and sea. And that's what causes more widespread thunderstorm activity there versus in the other locations in the Caribbean and Bahamas.